Okay. If I give you a function and I say to take the derivative with respect to a variable, but there are other variables, like what happened if you were taking the derivative implicitly and you came across to y? What would you have to write? dy dx. Okay? Like if I gave you x squared plus y squared equals 4, and I said, hey, take the derivative with respect to x, you would write 2x plus 2y dy dx, because y is a different variable than what I'm asking you to take the derivative with respect to, equals 0. Do you remember doing that? Okay, and we all can feel good about that, right? Okay, now, I made you panic. Don't panic. Okay. If we are taking the derivative with respect to t, the derivative of v with respect to t is dv dt. Can we handle that? Then we have 1/3 pi. 1/3 pi is a constant. So they hang along for the ride. But then r squared h. R squared h would be considered a product. So we are going to take the derivative of r squared, which is dr dt times h, plus r squared times the derivative of h. Why do you think I asked you to take the derivative with respect to t? It is time. And that's all we're going to be doing for about the next 4 days, is taking the derivative with respect to t. Okay? You don't like it? It's not. Okay? Now, did I expect you to remember how to do this? Not so much. Okay, this was a refresher. The x squared plus y squared equals 4. If you could remember that, you should be sitting in good shape. Okay? We'll get more practice with this. Now, much like optimization, related rates, it's all about word problems. Okay? So I have guided notes for you again, so you don't have to write down the word problems. Okay? But let me ask you this. And if you don't want them, then don't use them. But let me ask you this. What do you think of when you hear the word rate?
Slope.
Slope. What else? Time changing. Okay. Rate of change. Derivative. Derivative. Right?
Yeah.
Okay. So when we are given a problem that has to do with rates changing over time, if we are given a problem where we're talking about rates changing over time, we're talking about a related rates problem. If the radius is changing, how does that affect the circle's area changing? If a radius is changing and a height is changing, how does that affect the cone's volume and how it's changing? Okay. You are going to be able to pick these problems out of a crowd because it's going to be talking about rates. And it's going to give you rates or ask you for rates. Okay? So very similar to our optimization problems, you better draw a picture. Okay? Or one will be given to you. Now I know that there was one problem on our quiz that didn't need a picture, and that was fine. That was like one unique case. Related rates, you will always have a picture, okay? Because you're going to have to define variables, and there's going to be more than one variable all the time, okay? Any information that they give you, you need to identify. If they tell you that the radius is changing at a rate of 5 inches per second, then you know the RDT, the rate of the radius changing. Okay? If they give you information about the volume shrinking at a rate of 5 cubic inches per hour, they gave you information about dVdt. Okay? And so I want you to actually label those. Okay, you are going to have to find an equation, and that's going to have to go back to your picture. If you draw a picture of a circle and you label a radius, and then your picture is about A equals pi r squared, okay, they have to match each other. Okay. Once you have an equation, you're going to have to take the derivative. Okay, we can have as many variables as we want. Hopefully not that many. Because we're going to be taking the derivative with respect to t, okay? Every time. Your related rates problem will be differentiating with respect to t, okay? And then depending on what you have, you're going to evaluate to give me an answer, okay? Couple things I want to talk about here. If a rate is changing to where something is getting bigger, what kind of number should our derivative be? Positive or negative? Positive. If something is shrinking, then our rate would have to be what kind of value? Negative. Okay. We all okay with why that is? If something is shrinking, the rate is going to be negative because we're losing whatever it is that we're losing. Okay? So, what I'd like you to do is read that first problem on your sheet. What are we working with? What kind of a figure? A rectangle. So what should be in your picture? A rectangle. And in this rectangle, they keep referring to its length and width. Okay? So I'm going to label length and width. Okay, so where it says plan, okay, this is when we can kind of get an idea. What do we have? What do we know? What do we not know? What do we need to find? Okay, so what did they give us? Okay, the width of a rectangle is decreasing at a rate of 2 centimeters per second. What did they just describe? A rate, a negative rate. Okay, and it's the rate of the width. So since I labeled my width as W, they said that dW dt is negative 2. The length is decreasing at a rate of 3 centimeters per second. What can we label? Say it louder, Turner. We know that the derivative of the length would be negative 3 because that is the rate at which it is decreasing. Okay? And we're throwing negatives in there because we have decreasing rates. Excuse me. Okay? Ultimately, what are they asking for? At what rate of the at what rate is the area of the rectangle decreasing? So am I asking you for A? I'm asking you for dA dt. Okay, at what rate is the area of the rectangle decreasing? Okay, so I'm asking you for dA dt at the precise moment. Okay, the width isn't always 4 and the length isn't always 5, but at the precise moment that we have a 4 by 5 rectangle, what is the rate of the area decreasing? So I want to know dA dt when W is 4 and length is 5. Okay, that's the information that we know and what we need to find. Okay, so let's build an equation. If I need to find dA dt, what should my equation be about? Well, I can't build dA dt yet. I first need to build an equation about just plain old area. And how do we find length times width? And we have our picture. We have everything labeled. We've identified things that we need to know. We have our equation. Once we have our equation, we can take the derivative, always with respect to t. So dA dt equals be very careful, Emma. It's a product. Okay, don't get too excited. I know you're not the only one. We have a product, which means we have to do a product rule. I know that this looks a little bit different than what we're used to because we're used to like X's and Y's and not really L's and W's, but we have a product. So we need to derivative of the first times the second plus first times the derivative of the second. Andre, after we take the derivative, then we can plug in numbers. Okay. Maybe that's what you were saying. I don't know. I just heard you say plug in numbers. So I want to make sure we cannot plug in numbers until after we take the derivative. Okay. Since everything about our rectangle is changing, we have to take the derivative first. Now, we want to find dA dt. We know dL dt was -3. We know that we're looking at the rectangle when the width is 4, when the length is 5, and dW dt was -2. Okay, so what does that give us? -22. And if we're talking about our area over time, what would our label be for this problem? So centimeters squared would talk about our area, but we're talking about over time, and everything else in this problem has been percent. Okay? Now, you have found the answer, but what I would like you to do is convert that to a sentence for me. Okay? We are talking about the area, and what is happening to our area? It is decreasing. So the area is decreasing at a rate of 22 centimeters squared per second. Okay? I want you to interpret what you found, what it means. Is it increasing? Is it decreasing? What is changing? Okay, in this particular case, it was the area, and it was decreasing. I want you to interpret what you found. Okay. Take a moment. Debrief with your pod. What makes you excited about this type of problem? What makes you nervous about this type of problem? Okay. Now, one thing that I want to point out, and very similar to optimization, the more problems you do, the better off you are, okay? Every problem is going to be unique. Every problem is going to be just a little bit different. So the more practice we can get in, the more comfortable you're going to feel, okay? So you see that we have a quiz on Thursday. This is all we're doing until Thursday. Problem after problem after problem, okay? You're not going to feel comfortable right away, but you need to push through until you get that practice to really get the vision of where to go with the problem, okay? We're going to read a problem, this second problem. If you don't know how to come up with that picture, okay, right off the bat, it's okay. I want you to understand how we get the picture, and then when you come across a problem similar, you'll be able to get a picture yourself, okay? Go ahead and read through the next problem.
Will we need to convert the 5 minutes into hours?
You're going to need to convert something. Okay. So in the first problem, we probably all would have picked L and W for our variables because it talks about length and width. Okay. Here, when we draw this picture here, if this was something that was like a homework problem, I could see a lot of people having different variables. I'm going to use X and Y. Okay. We have two cars leaving an intersection, right? So here's an intersection. One travels north. I'm going to call that car X. And one travels, what direction?
East.
East. I'm going to call that car Y. Okay? So we have a right angle there. How fast is the distance between them changing after 5 minutes? So I do care about the distance in between them. Okay, so what do we know? We know the car traveling north is going 30 miles per hour. Is that a length or a rate? That's a rate. So dx dt is 30 miles per hour. We also know that the second car going east is going 40 miles per hour. Write down what we know there. Okay, ultimately, we want to know how fast is the distance between them changing. Okay, if I'm talking about a distance changing, what are we talking about? What kind of a value? Are we talking about a rate or not a rate? We're we're talking about a rate, okay? Those are the two things you got to decipher between. Are we looking for a rate, or are we looking for like a length or an area or a volume, okay? Any changing, the words changing, the words increasing, the words decreasing, and blatantly the word rate are the four words you kind of need to be on the lookout for. So in my picture, we are looking for dt. When our time is 5 minutes. Now, Andre, you noticed a problem right off the bat.
Minutes, while the other one's miles per hour.
Okay, we have a time in minutes. Everything else is in miles per hour. So we will have to keep that in mind. Okay, but we'll come back to that. Let's go to our equation. How might we be able to write an equation involving x, y, and d? Oh, the Pythagorean theorem. Okay, we have a right triangle. Let's use it. Okay. Now, there could be times when you're like trying to plan out what to do. You maybe don't know all of the work that you need to do in order to plug values in, and that's okay. You can come back to that step. Well, let's go ahead and take the derivative so we can kind of see what we need. Okay? If we take the derivative with respect to t, the derivative of x squared, 2x dx dt. The derivative of y squared, 2y dy dt. And the derivative of d squared, 2d dt. Oh, a lot of d's to try to say all in a row. Okay, well this is fine. Do we know dx dt?
Yes.
Yes. Do we know dy dt? Yes. We are looking for dd dt. So what in that equation do we still need to know to plug in? Okay, we need x and y. We're looking for this, so this is going to stay unknown. We have these two rates, but x, y, and d, we need to be able to plug something in there. Okay? Well, we have this information here when t is 5 minutes. So can we figure out how far car X has traveled after 5 minutes? Okay. What did you say, Eli?
I said 30 miles an hour is slow. Like, that is a painful speed sometimes. Unless you're in a neighborhood.
Okay,
Neighborhoods
which
are-
I would assume that these two are probably at an intersection, closer to neighborhood. Okay. Like this guy's on 96, but this guy's on Giles, right? 30 and 40 are appropriate speeds.
Giles.
I know. Okay, so how would I figure out the distance x after 5 minutes? How could I do that?
You can convert miles per hour to like miles per minute and multiply it by 5.
Or just convert minutes
5
to
minutes after.
or just convert it.
Okay, so if you are going to plug in 30 and 40, you're going to have to convert 5 minutes to hours. Okay, so how much of an hour is 5 minutes?
0.018.
Okay. Okay, so our time is 1:12. Our rate is 30 miles per hour. So after 1/12 of an hour, this distance would be what? Is it 2.5?
Yes. Yes.
You get that?
Yes. Yeah, I did that.
Yes.
How did we get that? Distance equals rate times time. Right? Back to science class. Distance equals rate times time. So if our rate is 30 and our time is 1/12, we're 2.5. Okay, 40 miles per hour. Rate times a time of 1/12 of an hour. What is that distance? 3.3 repeating? Okay, so let's keep that as like 10/3. Right? Okay. We have one more thing to find. How do we find D? Okay, we can come back up to our original. Sometimes this is going to happen where you're giving some measurements, but you need to find some measurements as well. You're going to have to come back to your Pythagorean theorem to figure out what the distance is at that time. So I'll let you go ahead and find that for me. You get 25/6.
Yeah.
Okay. If you take 2.5 squared plus 10/3 squared, and then you take its square root, your calculator gives things back to you in fractions if you ask for it. We get 25/6. Okay. Anybody want to guess what this is going to turn out to be? We have 30 and we have 40. What?
50.
Yeah.
No way.
What? I mean, it makes sense, right? Yeah. Yeah. Okay. So, you would write the distance between the two cars is increasing because we have a positive rate at 50 miles per hour. I want to get through two more types of problems. One has an angle, and I'm so sad because when it printed off, it like split up on the page. So some of it is on the bottom of the first page, some of it is on the top of the second page, and your picture got cut off. So read through and then draw your picture that I give you for number 3. Draw a picture because it got cut off. But this is a picture I would give you. We'll do it on the back. Okay. What are they asking us to find? The rate of change and the angle of elevation. So they are asking us to find d theta dt, right? Because they named your angle theta for you. And they want that 10 seconds after liftoff. So when t is 10. Okay, so in that information, is there a way to relate theta to S in 2000? Yeah. Yeah, with some trig. Which trig ratio? The tangent of theta is opposite over adjacent. Sorry. Okay. Now, some of you are thinking, Mrs. Hillman, we've never actually put in a number before. Okay. Is the distance horizontally from the rocket to the camera ever going to change? Is that distance ever going to change? Its rate is 0, not going to change. So if you have a rate that is not existent, like it doesn't change, you can plug that constant into your formula. That is fine. S is changing. Theta is changing. So those have to be variables. They have to. Okay. All right, so let's take the derivative with respect to time. What is the derivative of tangent theta? Secant squared theta. Oh, but please do not forget that theta is a variable that is not t.
What?
We took the derivative with respect to t. Is theta t? No, so we have to do our chain rule. Okay. Do you agree that this is like 1 over 2,000 times s? Okay. So when I take the derivative, we have 1 over 2,000 ds dt. Okay, so now we have that our time is 10 seconds, right? Well, how does that help us? Well, it kind of does, because they gave us something else. They gave us that S equals 50 t squared, right? So what would ds dt be? What? Okay, ds dt would be 100t. Well, if time is 10, we know that ds dt would be what? 1,000.
What happened to this secant squared theta? Is it still like?
Well, I haven't done anything with that one yet.
Oh, okay.
Okay? How do we figure out secant squared theta? Okay, we have a right triangle, right? We know that this guy's 2,000. If we plug in 10, because that's the time we were given, we know that this would be 5,000 because S is 50t squared, so plugging in 10 squared is 100 times 50 would be a 5,000. Okay, so if we did this is a right triangle, right? If we did the Pythagorean theorem with 2,000 and 5,000, we would get that ridiculous number for the hypotenuse, but that's okay.
6.
What's our secant ratio? How do we find secant?
1.
Hypotenuse over adjacent.
Yes.
So our hypotenuse over adjacent squared. Secant is the reciprocal of cosine. So it's 29 with 6 zeros. Okay. Now you could figure out what that angle is if you want and plug that in for secant and square it, but this is going to give you more exact numbers. Okay, so what happens is we get d theta dt. If you punch these all into your calculator, I'm just going to save you some time. I always want you to round to 3 decimal places as if it is an irrational number. 3 decimal places if it's an irrational number. And if I'm talking about an angle changing, first of all, we know it's per second. But what per second? Radians. Radians per second. Because we're talking about an angle changing, and so our angle is going to be in radians. Okay. We're going to look at one more, probably not get all the way through it, but the setup of it is important. So are there any questions before we do part of another problem? Can you get your, yes. Okay. I want you to go to the sand one. That's the next one, right?
Yes.
This is such an important problem. Please read through it and label anything that you find. Because it's an angle changing and an angle's measurement in radians. Because our ratios, if we can force it to degrees, but our ratios are. What do we know? We know radius equals height. What else? What rate would that be? 10 cubic feet per minute. Okay, so we know that dv dt is this. And we are looking for the rate of the height. At what rate is the height of the pile increasing? When? Oh, is it cubic feet?
Yes.
I don't know why I wrote centimeters. That was silly. When volume equals 1,000. Okay, so see my picture with my radius and height. It's not drawn very well because the radius does not look like the height, but that's fine. It doesn't have to be drawn to scale. Okay, we at least have a picture. It looks like a cone. Now, you're going to have cone after after cone after cone problem. So please remember that the volume of a cone is 1/3, oops, I'm thinking of a sphere, 1/3 pi r squared h. Ooh, I believe that's something that we looked at the beginning of class. Okay, now here's the deal with a volume of a cone problem. If we have to take the derivative, we're going to have a product rule. If the product rule is not necessary to take, like if we can change our formula somehow so that we don't have to take a product rule, that would be really cool. Do we have that opportunity to change our equation a little bit? We know that radius equals height. And we are looking for dH dt. Now, if we had information about dr dt, we would be okay. But if one or both of them are unknown, dr dt, I have nothing for it. I mean, yeah, in this case, it's the same as dH dt, but that's not always going to be the case. So if you have an opportunity to make a substitution in a radius height cone problem, it's going to be beneficial. I don't really want to take the product rule, so I'm going to go ahead and change this to 1/3 pi h cubed. If r and h are the same, then I can substitute r for h here, and h squared times h, please write it as h cubed, so you don't have to take the product rule. Now, I only have one variable on the right side for when we take our derivative. What would our derivative be? Pi h squared dH dt. Okay, I know we're getting close to the bell, so let me just say this. If we were to continue, do we know dV dt? Yes, we would put that number right here. We're looking for dH dt. We don't outright have h squared, but can we find h? Okay. They said when the volume is 1,000. So you could come here and say when our volume is 1,000, you could figure out what h is, so you can plug it in here. I would say about 50% of the time or more, you're going to have to come back to your original equation to find a value so you can use in your problem. Okay? Do I expect you to have this perfect? No. That's why we have 4 days on it. Do I expect you to try? I do expect you to try. So for each of the bolded problems, I better see at least a picture, and I better see numbers identified, like DTs of some sort, and I better see at least an equation with an attempt. Okay? If you don't have it perfect, we'll go over problems tomorrow. But you need to try. I feel like I need a few more rulers in here. You borrowed one.
Hey, chill, I'm in it. It's 12. Hey, at least yours isn't.